Good morning, everyone. So, recall that in the previous chapter we have discussed mainly about permutation and combination, or you can say that about arrangement and selection with repetition, without repetition. And we have seen that how do we address the problems related to arrangement and selection combinatorially. In this chapter, we will see that how do we address the similar problems, even more difficult problems, using the concept of generating function. So in this section, first we will see that what is a generating function. So to begin with, let AR be the number of ways to select R objects in a certain procedure. Then the generating function, which is denoted as g of x, is written as a naught plus a1x plus so on plus an x raised to the power n, where the coefficient of x raised to the power r gives you AR, which is the number of the ways to select R objects. To better understand, let's consider an example. So if we say that AR is CNR, where CNR represents the number of the ways to select R objects out of N objects without repetition. So what would be the generating function? Yes. So recall that we have discussed the binomial expansion 1 plus x raised to the power n, where the coefficient of x raised to the power r is NCR, which means that the generating function is 1 plus x raised to the power n. And what does it represent? So it is a generating function for finding the number of the ways to select r objects out of n objects without repetition. Yes, for better understanding, let's move further and try to compute the coefficient of x raised to the power 5 in the expansion 1 plus x square raised to the power 4. Yes. So if I have to find the coefficient algebraically or combinatorially, so since we do not know at this stage the algebraic method, so let's see the combinatorial method. So 1x square, there are 4 brackets are there, and for each bracket I may choose a term, may not choose a term. For example, from here let's say I choose x square, from here x, here I do not choose anything, or let's say I choose 1, and here I choose x square. So this is one way where I find a coefficient of x raised to the power 5. So it means that how many combinations would give me the coefficient of x raised to the power 5. So now I can say that this is what I am looking for. If I represent x raised to the power e1, so e1 means the powers for the first bracket, then x raised to the power e2, x raised to the power e3, and x raised to the power e4, and what I am looking for, x raised to the power 5. Yes, it means that I can say that I am looking for e1 plus e2 plus e3 plus e4 is equal to 5, provided each ei lies between 0 and 2. So the finding the coefficient of x raised to the power 5 get transformed into the another problem, which says that I need to distribute 5 objects into 4 boxes. So distribution of 5 objects into 1, 2, 3, 4 boxes, provided each box could have at most 2 objects, which means that this generating function for finding x raised to the power 5 into this one is the problem of distributing 5 objects into 4 boxes, provided each box has at most 2 objects. Yes, and this is what the generating function, this generating function represents. Yes, so the problem turns into number of ways of selecting R objects from 4 types with at most 2 of each type. So now you can see that how do we write down the generating function. This methodology gives you an idea that we can write down the problem into this form, and that gives us the required generating function. So let's see some exercise to better understand how it works. So find generating function for the number of ways to select R balls from 3 green, 3 white, 3 blue and 3 gold. So first see that how many boxes are there. So there are 4 boxes. If I put it as a distribution problem, and what is the condition? Each box has at most 3 balls, and to distribute R balls. Yes, so to distribute R balls, each box, so you can see that when I write E1 plus E2 plus E3 plus E4 is equal to R, where each EI, if you see the bracket, it would be x raised to the power 0, x raised to the power 1, x raised to the power 2 and x raised to the power 3. So 0 is less than EI is less than equal to 3. So now it's easy to write it down. 1 plus x square plus x cube, and the number of the boxes are 4. So this is the required generating function. After few examples, you will realize that you will be able to directly write down the generating function, but if it is taking time, you can use this approach by writing this equation and then you can move to the generating function. Find a generating function for the number of ways to select R donuts from 5 chocolate, 5 strawberry, 3 lemon and 3 donuts. So the first box could have 5 chocolate, 1 plus x square plus x cube plus x raised to the power 4 plus x raised to the power 5. The second would also have the 5 chocolate, could have the 5 chocolate, 5 strawberry donuts. The third one has 3, so 1 plus x square plus x cube, and 4 one is also 3. So which is the required generating function. Now if someone says that we need to select 6 donuts, then in this generating function we need to find the coefficient of x raised to the power 6, which we will study in the next section. How do we find the coefficient of x raised to the power 6? Now it says that repeat with an additional constraint that there must be at least one of each type, which means x raised to the power 0 is not allowed. So the generating function becomes whole square. Find the generating function to model the problem of counting all selections of 6 objects. 6 objects need to be selected from 3 types of the objects. So 3 types means 3 boxes are there with repetition of up to 4 objects of each type. So 4 objects of each type, which means till x is to 4 it is allowed, and 3 boxes are there. Yes, and in this we need to find the coefficient of x raised to the power 6. Now it says model the problem with unlimited repetition. In case of the unlimited repetition, the bracket goes on and goes on. Here the only observation is that this unlimited repetition is equivalent to 1 plus x square until x raised to the power 6 cube, because here I have to select only 6 objects. So either I write 1 plus x square plus x raised to the power 6 whole cube, or I write 1 plus x square so on whole cube. Both are equivalent. And in the next section we will see that it is more convenient for us to write down in this format. So here it is then, since we wanted only the coefficient of x raised to the power 6, thus greater powers of x could not be used. Yes, so that's all from this section. In the next section we will see how to find the coefficient of x raised to the power r in the generating function.